In this video, we're going to talk about estimating area. This comes about from a very natural problem. How do you compute the area of a region bounded by curves? If your region is a square or a triangle, that's easy enough. But how do you compute the area of a region bounded by curves that aren't straight? This problem dates back at least to the ancient Greeks, where they were very interested in computing the area of what we call conic sections. The conic sections included things like circles, ellipses, and parabolas, something like that. Let's focus on the parabola for the moment, because parabolas have reasonably simple equations that we can use to describe them. Let's start with perhaps the simplest parabola, which is the parabola having equation x equals y squared. Now, if we attempt to graph this parabola, it'll look something like this. And when I say I want to compute the area bounded by a parabola, I have to have some starting point and some ending point. I can start at the origin, but I can't leave the parabola open going forever because then it would have infinite area. So I have to choose some spot and just cut it off there. So I can choose any x value that I want so long as x is a positive number. Let's say we choose x equals 4. So what is the area of this parabola bounded by the equation x equals y squared and, let's say, x equals 4? If I want to find this area, what I can do is I can just look at the top of this parabola. Whatever the area is on top, the area on the bottom will be the same. So if I find the area of the top half, I can just double it and that will give me the area of the whole region. So that's what we're going to do. Let's redraw this, maybe make it a little bit bigger so that we can see a little bit more detail. Now, as it happens, I have an XY plane here that we can use. And what I want to do is I want to graph this parabola from x equals 0 to x equals 4, or at least the top half of the parabola. That's going to look a little something like this. There we are. That's the top half of the parabola x equals y squared. Another way we can write that is y equals the square root of x. So the top half of this parabola is actually the graph of the square root function. Our goal here is to estimate the area underneath the graph between x equals 0 and x equals 4. And a natural question is, how are we going to do that? Well, one thing that we can do is compute the area of a rectangle. So why don't we try to approximate this area using the area of a rectangle? One thing that we can be sure is that we can draw an area or a rectangle that contains the whole thing. So if I draw a rectangle with top at y equals 2, then I have a much larger rectangle which completely contains the entire top half of the parabola, or the area underneath the graph of the square root function. That, of course, is too big, but we can certainly compute it. This rectangle has area 2 times 4, which is 8. So what that tells us is the actual area underneath the parabola is less than 8. Well, certainly that's too much. We can see that there's a whole lot of area here which we don't want. So a natural question is, how can we improve on our estimate and get something a little bit better? And the way that we're going to do that is to use more rectangles. Let me just copy and paste this graph so that we don't have to draw it again. And let's paste it down here. What I want to do is I want to use not one rectangle, but several. For example, let's use 4 rectangles. What I'm going to do is I'm going to use 4 rectangles, each having base length 1. So, for example, the first rectangle is going to have base from 0 to 1, and then we'll have from 1 to 2, then 2 to 3, and 3 to 4. That's going to be, or those are going to be the bases of my rectangles. What I have to do is I have to determine how high these rectangles are. What I'm going to do is I'm going to start at the right endpoint of my first rectangle from 0 to 1, and I'm just going to draw a line straight up until I hit the curve. That's going to dictate the height of the rectangle. So this first rectangle is actually a square. It's 1 by 1. So this length is 1. Now the second rectangle is going to go from 0 to 1, or from 1 to 2 rather. So I'm going to look at the right endpoint, and I'm just going to draw a line straight up until I hit the curve, like so. That's going to determine the height of the rectangle. Now a rectangle is going to be flat on the top, and the left side is going to be the same height as the right side. So now we have a rectangle. How high is this rectangle? Well, the height is determined by the curve. As you can see, this line segment right here goes up until we hit the curve, and the curve above 2 is at y value square root of 2. So this length is square root of 2, because this is the square root function. Similarly, our next rectangle goes from 2 to 3. So I'm going to look at the right endpoint and just draw a line straight up until I hit the curve, like this. This determines the height of the rectangle. And again, the rectangle is flat, so we just draw a flat line and then bring it down because the left side has to be the same height as the right side. And again, how high is this rectangle? Well, it's determined by the curve. And the curve is the square root function. So the y value here is the square root of 3. The point is x value 3 and y value square root of 3. So that means y, which is the height above the x-axis, is square root of 3. So that's the height of that rectangle. What about over on this last rectangle from 3 to 4? Well, I've already got the line drawn in here. I look at the right endpoint and I go straight up until I get to the curve. The curve happens to intersect this line here at this point, where x is equal to 2 and y is the square root of 4. Sorry, x is equal to 4. I was getting ahead of myself. And y is the square root of 4, which of course is 2. So that means that this width, this height, is 2. So these are 4 rectangles which more closely approximate the area of the curve. We can compute the area of these rectangles. So rectangles have total area equal to, well, what is the area of the first one? Well, it's base times height, which in this case is going to be 1 times 1, plus the second one, well, the base is the same, it's 1 times the height, which is the square root of 2. And the next one has base 1 and height square root of 3, and the next one has base 1 and height square root of 4, which we can just say is 2. Now, if we add all these up, we're going to get approximately 6.146. This has a notation that we use to denote it. We call this r sub 4. Now, why do I call it that? Well, the 4 comes from the fact that I'm using 4 rectangles. What about this r here? This comes from the fact that I'm using the right endpoint of each interval to determine the height. So what I can see here is that the area of the rectangles is R4, which is approximately 6.146. This is what we call the right endpoint estimate, or the right endpoint approximation. Let me write that down. So R4 is the right endpoint approximation with 4 rectangles. That's what the 4 is for. I can also use the left endpoint. That's why we have an R. So you can also have an L. Let me just copy this graph again so we don't have to redraw it. And let me just paste it here. Now the first thing I want to do is get rid of all of these blue line segments, like so. All right. What I want to do this time, instead of using the right endpoint, is I want to use the left endpoint. So that's what we're going to do. I'm going to change the color to green, and we'll do that. Well, I'm going to still use the same base lengths of 1, but now we're going to use the left endpoints. So on the first interval, from 0 to 1, I'm going to not use the right endpoint, but the left endpoint. Now, the left endpoint is 0 in height, or is at 0. So there is no height here. So this is just going to be a flat rectangle. For the second one, from 1 to 2, I'm going to use the left endpoint, which is 1. And again, I'm going to draw a line segment straight up until I hit the curve, like so. That's the height of my second rectangle. So now I just draw a flat line and go down. So that's my second rectangle. My first rectangle was flat. It had 0 area. The second one has some area. In fact, it's a square again because the base is 1 and the height is 1. Now what about the next rectangle from 2 to 3? Again, I'm going to use the left endpoint and I'm going to go straight up until I hit the curve. Then I'm going to draw a line segment that's flat, and then I'm going to draw straight down. Now the height here is not 2, it's the square root of 2, just like before. And for our last interval, we're going to go from 3 to 4, so I go straight up from 3, and that's going to give me a rectangle, like so. And the height here, again, is determined by the graph, which is the square root function. So since x is 3, y is the square root of 3, and so that means the height here is the square root of 3. So if we want to add up the areas of these rectangles, that's going to be L4, since we're using the left endpoint, and it's going to be 1 times the height, which is 0, plus 1, which is the base, times the height, which is 1, plus the base is 1 times the height, which is the square root of 2, plus the base, which is 1, times the height, which is the square root of 3. So this gives us 0 plus 1 plus the square root of 2 plus the square root of 3. And this is approximately 4.146. This is the left endpoint approximation. L4 is the left endpoint approximation using, again, 4 rectangles. So the L here means left. And just like before, the 4 means 4 rectangles. Now, how do these numbers relate to the area? Well, if we scroll back up to the first one, we can see that our rectangles are all bigger than the curve. So if you add all of these areas up, you're going to get something which is a little too much. So what that tells us is that the actual area is going to be less than R4. So the area is going to be less than R4, which is approximately 6.146. Okay. And what else do we know? We know that these left endpoints give us rectangles which are a little too small, as you can see. These rectangles don't completely fill it in. We have some spaces here which don't quite get included. So what that tells us is that the left approximation is going to be too small. So L4 is less than the area. Now L4 is approximately 4.146. So what that tells us, if we put all this together, that 4.146 is less than the area underneath the curve is less than 6.146. Now, that doesn't tell us the exact area, but it gives us a range. We've narrowed it down. Now, we haven't maybe narrowed it down a lot, but we've narrowed it down to within 2, because we know that the distance between these two is 2. Now, that shouldn't be surprising, because if you look at the rectangles that we've added together, they're mostly the same. So here we have one of size 1 by 1, which appears here, and then we have the next one is 1 by square root of 2, which is here, and then here we have one that's 1 by square root of 3, which is here. What we don't have is we don't have this 1 by 2, which is 2. All of these are shifted over, and the 1 by 2 sort of falls by the way. So what that leaves us with is 2 less than the previous. Now, it doesn't always happen quite as nicely as that, but it's always true that the left and right sums are almost the same. It's just the left one has one sum on the left that the right sum doesn't, and the right sum, the right approximation, has one extra one on the right that the left ones don't have. So you always get this sort of thing happening. It might not always be a whole number like 2, but you always get this sort of behavior. So this gives us the actual area within 2 units. How do you get a better approximation? Well, to get a better approximation, simply use more rectangles. That's the idea. So I think we still have our image here. Let's erase some of these things. All right. So what I want to do now is I want to use more rectangles. So now let's double it. So let's use not 4, but 8 rectangles. So basically what I'm going to do is I'm going to divide all of these intervals in half. So now all of my intervals have length 1/2. All of these have length 1/2. These are going to be the bases for our rectangles. And how am I going to determine how high the rectangles are? Well, I can use right endpoints or I can use left endpoints. Let's start with the right endpoints. So I'm going to start with this endpoint, which is 1/2. And then I'm going to use the next, and that's going to give me the height of the first one. And then for the next one, from 1/2 to 1, that's going to have height 1, but now it only has width 1/2, like this. And now the next one is 3/2. I'm going to go straight up, like that. And the height of this one is the square root of 3/2. And the next one is the square root of 2. The next one is 5/2. So we just draw these rectangles. So this one is going to have the height the square root of 5/2, and so on. Square root of 3, and this is 7/2. So the height is going to be the square root of 7/2. And then finally, the square root of 8/2, which is the square root of 4, is going to be 2. Let's just write it as square root of 4. So all of these, again, have width 1/2, and all of the heights are the square root of whatever the x value is. So we can add these together, and we're going to have the right approximation, because I'm using the right endpoint, but it's r sub 8. And what is this going to be? Well, you're going to add in all of these areas. So it's going to be 1/2 by 1/2 plus, and then the next one is going to be 1/2 by 1, and so on. Now, if you add all these together, you're going to have quite a lot of terms. You're going to have 8 terms, and so it's going to be 1/2 times 1/2 plus 1/2 times the square root of, actually this is the square root of 1/2, sorry, square root of 1/2. And then it's going to be the square root of 1 plus 1/2 times the square root of 3/2 plus 1/2 times the square root of 5/2. And I'm running out of room here, but if you add all these together, you're going to get approximately 5.765. And again, this is a little bit too much because you can see that these things have a little bit more area than you want. So what you get is that the actual area is less than 5.765. You can do the same thing with the left sum, and the left sum you can show is approximately equal to 4.765. So in this case, it's going to be too small, so this is going to be less than the area, which is less than 5.765. So now we've narrowed it down a little bit more. The more rectangles you use, the closer the left sum and the right sum are going to be for this example. So to get a better approximation, use more rectangles. How do we represent that? Well, what we can do is we can just let the number of rectangles be an arbitrary number. So let n be the number of rectangles. Let's take our parabola again, or our graph of the top half of the parabola. Let's paste it here. So now what I want to do is I want to use n rectangles. Well, I don't know what n is, so I can't exactly draw them here with n, but let's just imagine that each one of these little rectangles here, one of these little rectangles gives us our width. So let's say that there are n of these. So the first one we're going to call x1, then x2, then x3, and it's going to go on like this until you get to x sub n, because you have a total of n intervals. So we're going to use n intervals. And each one of these, we can either use the right endpoint or the left endpoint. So if we use the right endpoint, we're going to have a little rectangle like this, and then the right endpoint, we're going to have another little rectangle, and so on. Now, because this is an actual example I've written down on graph paper, we could count them up, but let's just suppose that there are n. Now, the idea is that as you put in more rectangles, they get thinner and thinner and thinner, and they fit better and better and better, like so. Now, I'm not going to put all these in, but you get the general idea. Now, what is the width of all of these rectangles? Well, normally we denote it as delta x. So delta x is the width of the rectangle. Now, I can actually tell you what this is. Delta x is 4 divided by n. That's because the length here is 4. So this last one, xn is equal to 4. So the total length of this interval is 4, and I'm dividing it up into n pieces, so the length of each individual piece is 4 over n. So if I want to determine the area of all of these rectangles, That's going to be equal to, well, I'm going to add up all the areas. Well, all of these widths are delta x. So it's going to be delta x times the height. Well, what is the height going to be? This is the square root function, remember. Y equals the square root of x. So the first height is going to be the square root of x1. Then we're going to find the second rectangle, which has width delta x, and then the height is the square root of x2, and so on and so forth. Now the last one is going to be a rectangle whose right endpoint is x sub n. So the height here is the square root of x sub n. Now this is actually the square root of 4 because we know what x sub n is. But let's just write it in as the width delta x times the square root of xn, like that. Now all of these terms have delta x in them, so you can factor them out. So this is going to be equal to the square root of x1 plus the square root of x2, square root of x2, plus the square root of x3, and so on until we get to the last one, which is the square root of xn. And all of these terms are multiplied by delta x. So this whole thing is our r sub n, which in this case is just a little bit too much. You can also do the same thing with the left sums. So L sub n is going to be, well, if I start on the left, I'm going to start here at 0. Let's call that one x sub 0. So now it's going to be delta x times the square root of x0 plus delta x times the square root of x1, and so on. And now, if you look up here at our last interval, the last right endpoint is x sub n. So the last left endpoint is x sub n minus 1. And that's going to determine the height of our last left approximation. So that's going to be delta x times the square root of x sub n minus 1. And that's going to be our L sub n. Now there's a lot of plus signs here, and we have this dot 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 in the middle to indicate that there's a bunch of terms in the middle, many terms, because I don't exactly know what n is in this case, so I just have to use that dot dot dot. It's very common to use what is called summation notation to find an easier way to write it down. So the right approximation, r sub n, is equal to, and we write it like this, we use a sigma, the Greek letter sigma, to indicate sum. And the things that we're adding together are the square root of x, and then we put a little index here, I, times delta x, because all of the terms that we're adding together look like the square root of x with some index times delta x. So we write them down like this. Now the i's go from 1, 2, 3 up to n. And the way we denote that is we say the I equals 1 up to n. So whenever you see this, you read it as the square root of x1 times delta x plus the square root of x2 times delta x, and you keep going until you get to the top index, which is n, and so then you have the square root of xn delta x. The left sum, the left approximation, is similar. We're adding together things that look like the square root of xi delta x. The only difference is now we start with a different index. We start with x equals 0. That's our first index, x equals 0. And our last index is n minus 1, so we put that on the top, n minus 1. So this equals the square root of x0 delta x plus the square root of x1 delta x, and so on until we get to the last one, which is the square root of x sub n minus 1 delta x. The claim here is that as n gets bigger, you have more and more rectangles, which are thinner and thinner and thinner, and they sort of fit into the curve better. And so the claim is that the actual area under the curve is equal to the limit as capital N goes to infinity of r sub n, or in fact L sub n, if you use that. So we can approximate the actual area under the curve as nicely as we like by choosing a larger value of n. Now, none of these r sub n's or l sub n's will give you the actual area, but you can approximate it as closely as you like by choosing an n sufficiently large.